What's going on, guys? So I'm fresh out of the shower, and I wanted to talk about this cool philosophical debate that came up during one of my math classes earlier. For those of you who care, this is going to be the parents. You can see my Ogre cap, and I have a 9-star Marzensky. This is going to be an ace run. Okay, cool. So with that out of the way, I want to go ahead and talk about. Okay, well, I guess here's the deck as well. Uh, I want to talk about this professor of mine who said a very odd comment during the lecture. Now, this was last week, or I guess technically this week, or I guess last week, because it is technically Monday. It's recording this on Monday, 2 a.m. But okay. So this is a class called Formal Methods and something, man. I think it was just called Formal Methods. It's a computer science class that I'm taking right now, and it's basically all about logic gates, right? If you don't know what a logic gate is, it's those like and Q, P and Q, P or Q, not P or Q, and all that stuff. You know, the Boolean algebra and stuff. Very important in the world of computer science. Now, during this lecture, we were doing the truth tables. And if you don't know what a truth table is, basically, a truth table is like, let's say you have a bunch of switches, right? Let's say you have a bunch of switches connected together. And all of these switches are connected to one light bulb, right? And you got to figure out, hey, if I have all these switches flipped in this arrangement, is the light bulb going to be turned on, right? And for that, you can use a truth table. For example, how should I even explain this, man? I don't even know. Oh, damn, 4. So, anyway, we were going over the truth table for what was it? P implies Q. So, this is the if P, then Q statement, right? And the truth table for this goes something like this. If P is true... I need a pen and paper for this. Okay, hold on. So, the entire statement is P implies Q, right? It's written exactly like this, if you can even see it on the camera. So, in layman's term, what this means is, if P is true, then that implies that Q is also true. So, for example, I came up with a really good analogy for this. Let's say that in this case scenario, P is I ran out of groceries. And Q is I went to the grocery store, right? Now, obviously, if I ran out of groceries, as in if P is true, then obviously I have to go to the grocery store to refill, right? Then, therefore, Q is true. That means this entire statement is true. P implies Q is true in this scenario. Because, hey, it just so happened that when I ran out of groceries, I went to the grocery store, right? So that means P implies Q is true in this scenario. And the truth table for that would be like this, right? Now, in the world of Boolean algebra, we use the number 1 as true and the number 0 as not true. So, if we go ahead and look at my post-it note over here, you can see as long as P is true, and Q is true, then... Oh, crap. Excuse my little unorganizedness, but this is the entire truth table, right? If P is Q and Q is true, then therefore the entire statement that P implies Q is true, right? That's the truth table for it. Okay, cool. Cool. Very awesome. Now, let's say that, I don't know, P is true, but Q is not true. Well, then that means P does not imply Q, right? If I ran out of groceries and I didn't go to the grocery store, then that means running out of groceries doesn't cause me to go to a grocery store, right? That's basically the logic behind all this. Now, here's where the interesting thing happens. My professor proclaimed, and this is true, by the way, this is not where the problem begins. This is merely the setup to the problem. My professor proclaimed that if P is false and Q is true, then the entire statement is still true. Now, there's a very good reason behind why this is, and I'm going to explain it in a very non-informal... Oh my god. Sweet Tosho hint? Anything? Oh my days. My prayers have been answered. Okay. Anyways, there's a very formal way to explain this, which I do not understand. Or I just rather don't know the formal way of proving that. So I'm going to go over it very logically. Now, the reason why I got upset over this topic is because my professors got asked a question, right? A student raised his hand and asked the professor, hey, professor, in the truth table, you wrote that if P is 0 and Q is 1, then the entire statement is 1. And the student was wondering why that is so. And you know what do you know what my professor said to answer the student? He said, well, you see, some things in the computer science... Oh my fucking god, sleep deprived. Oh my god, Tazna might go. Get my mood up. Oh, thank god. So, my professor says that some things in life you just gotta take at face value and not worry about the why. He said, for example, any number to the power of 0 is 1. That makes sense. Yes, that does make sense. And the explanation for it is very easy. He also said stuff like, anything multiplied by 0 is 0. You got to take that for granted. Now, that was like, why? Why are you even saying that? It's like, no, there's a very logical reason for why any of these are true. So let me work in order, right? Let me work in order from the easiest to explain to the hardest to explain. So, the Gourmand? Gourmand? Suicide video tomorrow. I'm killing myself. Okay. So, there's a very good reason as to why all three of these statements are true. And I forgot to run the hopeful stakes. Oh my god, I should just kill myself already. Jesus Christ. There's a very good reason as to why all three of these are true. And, yeah. Let me start out with the multiply by 0, right? Any number multiplied by 0 is 0. Okay. When you say that a number... When you write down a number multiplied by a number, right? Very simply, let's say 2 multiplied by 1 is equal to 2, right? 2 multiplied by 3 is equal to 2 plus 2 plus 2, right? This. Now, the reason why it's like that is because the number you're multiplying by tells you how many of the first number there are. So 2 times 1, there's 1, 2, right? If I would say like 2 times an apple times 1, there's 1 apple. When I have 2 times 3, there's 3 2s, right? And when I have 2 times 0, there's no 2s. And since there are no 2s, there's nothing, right? There's nothing at all. That's basically the entire logic behind why a number times 0 is 0. Okay. Very simple, right? Very simple. Geez, I want to take this training so bad. Okay. So that's very easy. Let's talk about a number to the power of 0. So as we know, a number to the power of another number is pretty much the same as addition to multiplication, but except this time it's multiplication to power, right? When you multiply a number by a number, you add it that many times. When you raise a number to a certain power, you multiply it that many times. So 2 to the second power is 2 multiplied by 2, 2 times. You know, there are 2 2s, and they're all multiplied together. Okay, cool. We have come to an agreement. Okay, so why is a number to the 0th power 1? Okay, well, for that, we're going to have to go into very, very basic algebra, right? So let's say that we have 3 to the second power divided by 3 to the first power. Exactly like this, in this form, right? 3 to the second power divided by 3 to the first power. That would be the same as 3 multiplied by 3 divided by 3, right? And as you can see, since these are all multiplications and divisions, we can cancel it out. This is basically the same thing as, hey, I'm going to take 3, I'm going to add 3, and I'm going to subtract by 3. Since there's an addition by 3 and a subtraction by 3, then they cancel each other out, right? It's a very informal, canceling each other out is a very informal term in math, but that's basically what they do. So same thing with this problem. The multiply by 3 and the division by 3 cancels out. And thus we have 3, right? Okay, cool. Well, I mean, technically they don't cancel each other out and completely go away. They actually turn into a 1, right? A pretty easy to understand form might be actually expanding it out to this bottom form right over here. So 3 multiplied by 3 divided by 3, that's just going to equal, of course, 3 multiplied by 1, which is, of course, 3, right? Okay, so we've come to that same idea. Now, the reason why this makes sense is because if you look, well, 3 to the second power, right? The same, the law that's derived from this logic is that whenever you have a power with the same base, as in the 3, the base number, the same base to different powers, and they're dividing each other, you take the top exponent and you subtract the bottom exponent. So this, when you see 3 to the second power and 3 to the first power, basically, you take the 3 to the second power and you subtract it by the power of the bottom number. So the top number here was 3 to the second power, which is 2, and then you subtract 1, right? So it's now 3 to the 2 minus 1 power, which is 3 to the first power, which is 3. Okay, cool. Now that I've lost about exactly half of you guys, and none of you are paying it. Jesus fucking Christ. What did I do to deserve this? Okay, now that I lost half of you, and half of you guys are still with me, let's look at the scenario where it's 3 to the third power divided by 3 to the third power, right? Exactly written like this. Now, using the previous method, we can see that, hey, it's once again a division problem, right? You know what we can do? We can just subtract the top power from the bottom power. So 3 to 3 power minus the 3 over here. Then that would be what? 3 to the 3 minus 3, which is equal to 3 to the 0 power, right? 3 to the 0 power. Okay, cool. We have written 3 to the 0 power in a very particular way. And you might be wondering, why does this matter? I'll show you why this matters, because we're going to write it in a second form, or a third form, I guess. So the third form is going to be 3 times 3 times 3 divided by 3 times 3 times 3, right? And that can pretty much be divided into this. So you can see the bottom over here, this monstrosity I've written. This basically expands out to this bottom one here. And if you take this one and use and you split it apart, it turns into a bunch of 3 divided by 3 multiplied by 3 divided by 3 multiplied by 3 divided by 3. Which is what? 1 times 1 times 1. And what's 1 times 1? 1. And what's 1 times 1? 1. There you go. We have concluded that 3 to the 0 power is 1. And thus, using the same proof, we can say that every single number to the 0th power is, well, sorry. 1. 1. There, I'm holding up a finger. 1. Not 0. Not 0. 1. Okay. Cool. So, now that I have absolutely destroyed and demolished my professor, I want to discuss the truth table, right? Why does... Oh, fuck me. I need to get rid of Night Owl, like, right now. Tazuna, go. So, why is it that... Rice, what are you doing? I'm going into summer camp with... Karaoke? So cooked. Wait, it's salvageable! Oh my god, claw machine. I forgot about claw machine. Okay. Hold that thought for a second. So go back to the vending machine example, right? The entire point is not the vending machine example. The oh my god, did I get this? Going back to the grocery example, P implies Q, right? We said that P is you. That is a Daiwa speller with like two other. We said that P is you ran out of groceries, and Q is you need to go to the grocery store. So, oh my goodness gracious. So when discussing the... Holy crap, I just got all of them. That's crazy. Jeez, I'm getting so sidetracked. It's not even funny. I'm not gonna get that blushing. So when we're discussing the law that when P is not true and Q is true, then P implies Q is true as a statement. The reason that works is because when we think about it from a broad point of view, just because you ran out of groceries, or, well, just because you didn't run out of groceries, as in you had a bunch of groceries and you went to the store, doesn't disprove the fact that you go to the grocery store when you run out of groceries, right? So the entire thing is we're trying to prove the statement. We're trying to prove the entire statement, the entire premise, the entire line of logic that when you run out of groceries, you go to the grocery store, right? That's a very obvious thing that happens. You go to the grocery store. But oftentimes, we don't go to the we go to the grocery store even though we haven't ran out of groceries, right? Like maybe it was one specific thing you needed that you forgot to get during your groceries, but just because you went to the grocery store when you had like when your fridge was full doesn't disprove the fact that you still go to the grocery store when you run out of groceries, right? The entire point of that statement is that it's basically saying, hey, I don't have enough information to... Oh my god, Rice Shower. Please, for the love of God, if you... We're not even in senior year yet, and I've had 4 mood down events. I know one of them was from Night Owl, and that's on me. I should have gone to the infirmary, but holy shit. Jeez, okay. Whatever. The entire point of this proof is that the statement... I don't even know, man. Oh my god, Rice Shower has completely thrown me off. Okay. I need to like organize my thoughts and write this out again, right? So, we have the statement P implies Q, and we have the truth table. P is not true, Q is true, and we have the entire statement P implies Q is true. Okay. Bear with me now, guys. We're almost done with the run. So we have this, right? We have this scenario. We're trying to figure out why the top one is true and why the bottom one is not true, right? Necessarily like right over here, right? Why the entire statement is true for the first one and the entire statement is false for the second one. Now, the thing is, on the bottom one, when you run out of groceries and you don't go to the grocery store, then that means running out of groceries is not a reason for you to go to the grocery store, meaning that the entire statement that running out of groceries means you have to go to the grocery store is false, right? The entire statement is false. That's basically what it means. Okay, so what about the top one? The top one, right? We have a bunch of groceries. We didn't run out of groceries, and we still went to the grocery store. Well, this is true because these two conditions are actually not enough to disprove the bottom one, right? It's not enough to disprove the entire statement. Just because I went to the grocery store, even though I was full of groceries, does not mean that I don't go to the grocery store when I run out of groceries as well, right? That's a different scenario in and of itself. So yeah, that's basically the entire premise of why I got upset at my professor. Because the thing is, I mean, like, how long did this take? 20 minutes? We have an hour, right? We have like an hour of lecture in class, and he didn't bother to take the time to explain it. And the thing is, it took me 20 minutes to explain it to you because I'm literally giving you all of the groundwork, right? Every piece of prior knowledge that you needed to know in order to understand me, I just explained it to you so that I can get on with exactly what I was trying to describe. But for my professor, he's in a room full of 300 level students, which means that they are all, every single one of them is a junior. And when that happens, you can cut a lot of corners, right? You can cut a lot of corners in your explanation. Your class is going to know a lot of stuff. So I'm just upset that he didn't take the 5 minutes to explain why this is a true statement. That's basically what I was upset about. And I guess the overarching theme of the story is that should you entertain every single idea? What I mean by that is, I'm going to defend my professor a little bit here, even though I'm upset at him, and I should be upset at him, and I'm completely in the right to be upset at him. I'm going to villain chair, right? To be fair, my professor is teaching a class of, oh my god, Charming, are you serious? Thanks, I can build friendship faster with my support cards who I've already maxed out friendship with. The reason I'm upset, no, sorry. I was villain chairing. I was arguing for my professor. To be fair, in his defense, right? He is managing he's not managing a classroom. He's managing a lecture hall, right? And the difference between a classroom and a lecture hall is that a classroom, you can hear when the person in the back kind of whispers. But in a lecture hall, the person sitting in the back needs to scream at the top of his lungs for the professor to hear him. So obviously there's a difference in the size of a class, right? There's a difference in the size of the density of the students he's teaching. He's teaching like hundreds of students, right? He's giving a lecture in front of hundreds of students. So maybe going on like a 5-minute tangent on something that maybe like only one person was confused on is not really a valid choice of words. Not a valid choice of action, right? Not an intelligent idea, I should say. Maybe. So obviously there's that argument, but I guess the entire philosophical debate is like, when should you explain these menial things? Because I did talk about it for 30 minutes, but this is a very small thing. My professor is kind of correct in that you don't necessarily need to question every single postulate every single theorem, every single law in mathematics, right? Especially so in mathematics. You don't necessarily need to question them all. You can just take a lot of them at face value and be on with your merry way. Be on your merry way, right? It's not really going to affect you. It's not really going to harm you in your journey of understanding math. It's not really going to halt your learning in any kind of way. Which I agree with. But at the same... Oh, fuck, bro. Why didn't we go to the shrine? Okay, well... The thing is, I'm going to have a very biased opinion about this sort of a debate. What? My dog's friggin' knocking his bucket of toys over. I'm gonna have a very biased viewpoint towards this topic of discussion because the thing is, I'm a math tutor. Holy, that's 4 support cards on Wit. Because I'm a math tutor, so most of the time when I'm teaching something, I'm in a one-on-one scenario, one-on-one situation, or I'm in like a 1-to-4 scenario, right? It appears he's found his favorite toy. Holy guts training. Can I hit this? Oh my god. Yeah, so I've never had to deal with a scenario where I've had to teach more than 30 kids at once, but that was like in the extreme. God damn, how many sleep deprived am I gonna get? Whatever. You know, it's like in a very normal case scenario, I don't have to deal with more than 4 kids at a time. So I have all the time in the world to be like going into the nitty-gritty details and yeah, and explaining all the small things to my students, right? Whenever they ask me any sort of these like postulates, I can go on a very, very short side tangent with them and explain it to them very clearly. Oh my goodness gracious. So obviously, I'm going to think that, yes, you should entertain these ideas and you should entertain all these small questions because it's going to support learning, right? It's going to support the why. It's going to oh my fucking god. The entire point of math is that it's teaching you problem solving, right? In a standard problem solving environment, you have a problem at hand. Let's say, for example, your fucking wall broke down. I don't know. And you got a bunch of tools to work with, right? You got a bunch of drywall, you got a bunch of that pink paste, and you got like a couple of beams of wood, and you got to fix your wall, right? That's problem solving in a very engineered... Oh my fucking god. How did I fail this? I should probably like set myself as a front runner. That's like a very classical thing for problem solving, right? A very classical scenario. In mathematics, the analogy is that the broken wall is the problem you were given. And the tools are the laws, right? The laws of math. All of the postulates, all of the rules, like the distributive property, associative property, laws of integration, laws of derivatives, the formal definition of a derivative, everything like that, right? And it's up to you to use those tools in order to reach the solution, right? Which is, in this analogy, a fixed up wall. And when a topic is so heavily centered around problem solving, when you tell your student that you should just look at this theorem and take it at face value and just know that it's going to be correct, even though you don't understand why, is a fucking idiotic thing to do. It is genuinely the single most foolish, utterly disgusting, ignorant, and pathetic thing you can teach to a student. To look at something and take it at face value and ask no further questions. When I see a teacher, when I see an educator, in fact, when I see an educator do that, it makes me boil. It pisses me off to the highest degree. It's absolutely embarrassing that you, as an educator, think that this is a good idea. It's detrimental to your students' learning. It's detrimental to your students' future. It's disgusting. It's quite frankly disgusting. But I see where he's coming from. He's in a classroom, not even in a classroom. He's in a lecture hall where he has to teach 300 students at once. And there isn't a lot of time to entertain a lot of these small ideas, because otherwise what's going to happen is all 300 students are going to raise their hands and ask these bullshit questions. Well, it was closer to like 100 and it was closer to like 100 students in the lecture hall. But 300 is the number of students he has to teach on a weekly basis, right? Because that's all of his sections combined. He doesn't teach one class. No. He's a professor. He teaches 3 other classes, right? And all of those classes have 100 students each. And can you imagine the amount of time that would be wasted if every single one of them were to ask him a question like this, and he had to entertain each one of these small ones? I mean, that's why office hours exist, right? But at the same time, learned helplessness is a real problem, learned helplessness is when students are too afraid to ask a question and they just pretend that they understand everything, right? Learned helplessness and shit. It's just, I don't know. I got incredibly pissed off. How is this a B plus? Holy fucking shit. I just got so pissed off when he said that there are some things you got to take for granted in the math world. It's like, no, that's not how it works. The entire point of mathematics is that everything has a reason why it makes sense, right? And when it doesn't make sense, when you can't figure out a reason as to why, we say, well, fuck it. It's undefined, right? Like 0 over 0, 0 divided by 0. What's the answer to that? Oh, I don't fucking know. So we just write, I don't know, right? I don't know. That's just what I wanted to talk about. Let me know what you guys think about this. I mean, I'm curious to hear it too.